Greetings everyone, my name is Mark William M. Talens and I will be your guide today as we learn something new and exciting. Electroactive polymers. Under an electric field, these materials will change their size or shape. One type of electroactive polymers is dielectric elastomers. These expand when given electricity. The elastomers is sandwiched by electrodes. These charges attract and cause a change in shape. Another type of electroactive polymers is called ionic gel. When electricity passes through, the cations move to the cathode. So what they can do? Here's a video of what they can do. Amazing, isn't it? It really makes you wonder, how does it move on its own? The clips you just saw are called electroactive polymers, or EAP for short. Today, we'll be tackling all about it. So sit back, relax, and enjoy what you are about to discover from this lecture video. Electroactive polymers are polymers that change their size, shape, or volume in response to a strong electrical field. In the field of active materials such as piezoelectrics, thermoelastic polymers, shape memory alloys, and polymers or magnetostrictive materials. Electroactive polymers stand out due to their large active deformation potential, high response speed, low density, and improved resilience. They are extremely lightweight, inexpensive, fracture tolerant, and compliant. The most common applications of this material are actuators and sensors. What is an actuator, you may ask? An actuator is a device that produces a motion by converting energy and signals going to the system. On the other hand, a sensor monitors conditions and signals when changes occur. These two often work hand in hand together, but they are essentially opposite devices in the vital part of the next phase of industry. For us to have a deeper understanding about electroactive polymers, let us talk about its brief history. The first reported occurrence of an electroactive phenomenon dates back to 1880, when William Röntgen observed a light change in a fixed rubber band with a weight on its one end, when being electrically charged and discharged. In 1899, F.E. Sacerdote confirmed Röntgen's experiment and formulated a theory of the strain response to electric field activation. In the early 1990s, ionic polymer metal composites were developed, which displayed much better electroactive properties, much lower activation voltage, larger deformation than previous EAPs. The first commercially developed device containing EAPs as an artificial muscle was a fish, being able to swim on its own, produced by EMX in Japan in 2002. It is very fascinating to note that a simple discovery before have made a huge difference in innovation in our world today. Now, let us learn more about some of the things that electroactive polymers can do. Artificial muscles. Their ability to emulate the operation of biological muscles with high fracture toughness, large actuation strain, and inherent vibration damping draw the attention of scientists in this field. EAPs have even successfully been used to make a type of fan. Aviation industry. The electromechanical properties of electroactive polymer materials endow them with the capability to work as both sensors and actuators in the field of aerospace. Hence, we provide an overview of various applications of electroactive polymers in the aerospace field, notably aircraft morphing. Soft robotics. The natural muscle-like operating principles of the actuators make them ideal for biologically inspired robotics projects. Advantages include the ability to manufacture in nano and micro scale, low energy consumption, and higher force output as compared to weight, and their ability to operate silently and in different environments such as water and air. Let us first talk about seals and how it is important for us to understand its function. Seals are components in static and dynamic systems which are responsible for preventing leaks, maintaining system pressure, and preventing contaminants from entering the system. Seals are primarily composed of rubber because of its advantageous mechanical properties, including its flexibility, high bulk modulus, resistance to cuts and tears, long fatigue life, ease of manufacturability, and its low cost. Resealing a leaking gland or reducing the amount of leakage would give the operator a time span in which to order a replacement seal and prepare for a shutdown of the device. This will result in prevention of certain types of catastrophic failures. Billions of O-ring seals are produced worldwide each year, and they're responsible for the livelihood of many mechanical systems used daily. They are mostly used in static and dynamic systems, which encompasses a wide range of industries. In a typical design, the O-ring is placed into a gland, and the seal is compressed to achieve a non-deformation. The compression results in mechanical stress at the O-ring surfaces. As fluid flows through the O-ring, fluid pressure develops. As the pressure of the fluid increases, the stress on the surfaces increases. As long as the stress on the O-ring is larger than the pressure from fluid flow, the O-ring will not leak. Unfortunately, O-ring failure and resulting in leakage can occur to a number of mechanisms primarily, including improper installation and mechanical damage. Achieving this goal has very important implications in various types of industries where seals are used, including the medical industry, automotive, aviation, aerospace, appliances, and many others. The device is made with flexible materials that are designed to withstand high heat and pressure, making it suitable for most applications. The ability to reseal leaks dynamically provides a novel advantage in systems where immediate shut-off or repairs are not an option. It's incredible to see where research and exploration can take us. Let us all keep looking for new ways to improve the world through research and innovation. That's all for today, everyone. I hope that you have learned a lot from me. Once again, this is Mark William M. Talens, and thank you for listening.